George E.P. Box is actually a famous statistician from a while back, and he said essentially all models are wrong, but some are useful. Not exactly a joke, but still useful for our lesson today. The fact that we will be using the t-distribution, it won't model everything perfectly, but it's the best we can do with what we've got. So let's go ahead and revisit. There's not a lot changing today. So we're doing a modeling for a sampling distribution of means. And we're looking at the difference of the means, right? So we have y bar 1 minus y bar 2, just like we did before. What's the difference now? Well, when we're doing two samples, remember we had to do the Pythagorean theorem of standard deviation. So we have to square the standard deviations or the variance and add them and then take the square root. So anyways, we got this formula right here from that. The only thing that's changing is instead of using standard deviation, because I don't know it, I'm using the standard deviation of the sample instead of the population. The critical value t, if we need to look it up, would be inverse t. Now, honestly, we're gonna be letting the calculator do almost all the work on this. There is a rule of thumb where you can use, look it up with your from the table, using the degrees of freedom, which is the smaller of either your first sample minus 1 or your second sample minus 1. But the problem with doing this is you tend to go too conservative on your degrees of freedom, so your confidence intervals start to get so wide they're not that useful. So you could calculate a more precise degrees of freedom right here. So if you're feeling adventurous, you can go ahead and do this. I was just at a workshop and they were telling me how in China there was one group of students and they all calculated this by hand and they did it correctly. But there's no reason for you to do that. Let the calculator do it, okay? So let's go back over conditions and assumptions. We have the nearly normal condition, and that's the trickiest one for this kind of data. First of all, always plot the data. If n is less than 15 or so, the data for both sets should look normal, and there should not be outliers. An outlier can disqualify your data. Now, that said, let's say you do have outliers, and you're like, okay, do I stop doing the problem now, or do I keep going? Keep going. Do the problem, because you can always say, hey, my results are suspect, or I could look at the data without the outlier and look at the data with the outlier. So there are a lot of things you can do to explain some aberrations in your results because of the outliers. So whenever doing a problem, if you say, oh, the conditions are not met, go ahead and say the conditions are not met. Do the calculation and note the issue. For n is greater than 40 or so, you can use this model even if the data are skewed. We're still not too fond of outliers, but we're okay with the skewed. And in between, you need to confirm that both sets of data are unimodal and symmetric. All right. Now, their definition of unimodal and symmetric, it's not like it's going to look perfect, like a beautiful little peak in the center. It could be a little bit bumpier than you think. Okay, finally, independence on assumptions and conditions. The data must be reasonably random and drawn independently, or if it is an experiment, the subjects were randomly assigned to treatments. So be careful before and after treatments. Those are not independent. So you know how I'm trying to look at my geometry students from the fall compared to the spring? That would not qualify for this analysis because they're the same kids. They're not independent. Be careful of matched pairs, husbands and wives, and that would be kind of the same thing. If there's any sort of linkage between them, they're not independent. Okay. Now the 10% condition, usually we're dealing with small samples anyways. It's not normally an issue unless we're dealing with very large samples or very small populations. So in this, for today's lesson, we're calculating the two-sample t interval for the difference. So when the conditions are met, we are ready to find the confidence interval, which looks a lot like before. It's basically the difference in your means, right? Because that's what we're looking at is differences of means, plus or minus your critical t-value times the standard error, all right? Notice that the t-value depends on the confidence level and this. But again, let your calculator do it. I am not going to look up a single t in today's examples for good reason. Not only that, you'll notice when the calculator does it, you will get a non-integer degrees of freedom from that fancy formula, which is more exact. So just let the calculator do it. Okay, so let's take a look at an example. Resting pulse rates for a random sample of 26 smokers had a mean of 80 beats per minute and a standard deviation of 5 beats per minute. Among 32 randomly chosen non-smokers, the mean and standard deviation were 74 and 6 beats per minute. Both sets of data were roughly symmetric and had no outliers. Determine the 95% confidence interval for the difference in pulse rates for smokers and non-smokers. By the way, do you think this is an experiment or a study? I would dare say it's a study. We're not doing anything to them. So, and we're just sampling. Okay, so is it random? It's given in the problem. Okay, it's not always given in the problem, but this time it is. Independence. That's pretty reasonable for this sample. We don't think that the smokers were trying to prod the non-smokers to have higher or lower beats per minute, and vice versa. Nearly normal condition. Well, they told us the data is roughly symmetric and had no outliers, so we meet the nearly normal condition. So let's go through the calculations. Well, basically, I wrote down the values. I've got the average or the mean, the number of people in each sample, and the standard deviations for those samples. And I could actually show the standard error and calculate it. But this confidence interval, this t of 56, right? And you're probably going, let's see, where the heck did they get 56? Honestly, they got it from the calculator, which is where I got these numbers. So let me show you how to get that. First of all, you want to hit Stat, go to Test, and we are going down to two sample t interval. So you can see it's right there at 0 on my calculator. And I want statistics, stat. So I put in the mean for the first sample, the standard deviation, which I'm looking up. There we go. And then the sample size, mean for the second sample, the standard deviation, and the sample size. Now you see confidence level, it's going to ask you pooled or not pooled. Never do pooled, just do calculate. Just don't do pooled. And we'll talk about that some more. So you can see it did calculate everything for me. There's my confidence interval, 3.1 to roughly, oh, this one gave me 8.89. A little different. I must have a typo here. All right. So basically, oh, it was supposed to be 8.89 on that slide. So resting pulse rates for a random sample of 26 smokers had a mean of 80 bits per minute and a standard deviation of, oh, so anyways, we are 95% confident. The average pulse rate for smokers is between 3.1 and 8.9 beats per minute higher, always compare, than non-smokers. And you want to keep this statement pretty simple. If you try to get too fancy on your interpretation, usually that's just going to get you in trouble. So just keep it simple here. All right. Let's go ahead and look at another example. This time I'm giving you a list of data and saturated fat content for several pizzas sold by two chains. And this is all the information we had. So let's look at the conditions. The conditions, the two samples were chosen independently of each other. So we're pretty sure that, you know, we didn't, the samples we picked at brand PJ did not have any influence on brand D. Random, there's no mention. So what you want to do here is instead of stop working and say, oh, I don't know if these are random, we're going to assume the pizzas are representative of all pizzas by these two chains. And if after you write your conclusion, you're like, well, this is based on the assumption that those pizzas are representative, it is perfectly fine to write that. Okay. Nearly normal conditions. Both distributions are roughly unimodal and symmetric. So these two distributions, and remember your histogram can change depending on your settings. So these histograms have pretty kind of normal settings, windows of 2.5. This one has windows of 2.5 as well, doesn't it? 2.5, 4.5, actually 3. Let's see, what do we got here? 4, 2. This one has windows of 2. So remember your shapes are going to change a little bit as your windows change, but this was considered good enough to be roughly unimodal and symmetric, okay? So we'll go ahead and do the mechanics. Here's the information on pizza brand D, which I basically get by entering my data in the calculator and either going ahead and doing an individual confidence interval or doing one var stats. You just do one var stats would be easier. And then we have our standard error calculation, which I went ahead and did by hand. And then our confidence interval, which honestly, I let the calculator do all the work for that. So this is how they're showing the work. You could show this when you're writing down your response, and then you could look up this number, the degrees of freedom, from the calculator. So this time we're doing it from data, which is actually easier. So I have my data that I already entered here, and then I press stat tests, and I go down to 2-samp t interval. Enter. And I make sure I go to stats. Oh no, I got a list this time. List 1 and list 2. No pooled. Hit calculate. See how much faster this is? And the calculator thinks and spits out my confidence interval. So you can scroll down, see the sample size if you need to. And all your data, and my degrees of freedom are right there too. 32.8, which is what is written here. Okay, one last, and then the conclusion, because we always need to interpret. We are 95% confident that the average saturated fat content for brand D is between 2.73 and 6.71 grams higher than the average saturated fat content for brand PJ. So it sounds like we're always saying the same thing, but it's pretty safe to write your interpretation this way, so I would go ahead and stick with that. One last thing. When you're comparing two things, it might be tempting to say, hey, if the intervals overlap, then there's no difference. Well, so this example, we've got 2 diets for pigs, and we did the confidence interval for diet A and for diet B, which I could do on my calculator. I'll show you how to do that again in case you forgot. And you can do it from statistics. So the problem with this, if I just assume that if the confidence intervals overlap, there's not much difference, that rests on the assumption that the 2-pound difference is smaller than the sum of the 2 separate margins varied. But the thing is, we're supposed to sum variance. Remember, we're supposed to do Pythagorean theorem of statistics. And a quick way of showing that is one Pythagorean triple in geometry is a 3, 4, 5 right triangle. Well, you'd be tempted to say, well, 3 plus 4 is 7, but the hypotenuse is really 5. So you would be overestimating how big your intervals are for the difference. And so we can go ahead and calculate on our calculator. This is the actual interval I got. Well, since it doesn't include 0, it doesn't look likely that the diets produce the same results. So again, you can see here, if I just look at these, I think, they're pretty much the same. But if I look at these two, oh, okay, definitely one of the diets definitely produces more weight gain than the other. Well, we're never sure of anything, but we're pretty confident. And we're going to go ahead and do the calculator, and you're going to notice, so I'm going to put in the stats again, 2-samp t interval. Oh, well, here I'm doing one interval just so you can see how I calculate it. So you can do it for just one interval when you're looking at the data. And I put in diet A. We had 36 pigs. And I'm just doing 95% confidence since that tends to be our default. And you can see that I pretty much match the data from the book. All right. And then I'm going to go ahead and do the 2-samp t interval and put in my data, since that's what my stats, since that's what I have instead of data list. Here you see my mean was my mean weight was 53, my standard deviation 4 and 36, confidence level, don't pool, hit calculate, and voila. My interval is 0.34 to 3.66 pounds. All right. So again, doing these confidence intervals should feel like more of the same. What's the difference? We got this weird degrees. Well, first of all, compared to the first time we did the difference of 2 means, Then we had the standard deviation for the population. Now we're using the standard deviation of the sample, which means we're doing a t-distribution. And the extra wonky thing on this is that degrees of freedom can get really wonky on you. Look, I've got 64.9, roughly 65 degrees of freedom on this problem.